Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to start looking inside some of those sections and segments from our ELF file. So we showed you how to use read ELF in some previous videos in order to look at the different headers, and now we're going to show you how you can look inside those. So we'll start by using our old friend, read ELF. So remind ourselves of the sections available. I'm going to do a read ELF section headers on Xingxi bind shell. Here we can see various sections. So we have some notes in 2 and 3. Our text section that contains our code is in 13. And we have some comments in 26. So let's use read ELF to look at some of these. The syntax is pretty easy. Read ELF -- hex dump equals, and then the number of the section to dump. So I will dump section 3 of our file. And there you have it. You can see that this contains new and then some other information that is not necessarily ASCII text. What about section 6? Section 6 has a whole bunch of strings. This is in a string table, so you can see some of the strings related to this program, such as libraries that are being loaded, function calls, etc. We can have a look at 26, and this is a comment, and it tells you the exact version of GCC that was used in order to compile this program. What about the text segment? We talked about this one before, and we said that it contains the code for your program. Let's go ahead and dump it and see what it looks like. So here is a dump of our text segment, which is a somewhat longer segment, and you'll notice that this dump is incredibly unuseful. The reason for that is that it just dumped the raw hex and any ASCII interpretation. But that's not what we're looking at here. We're looking at source code. So we want to use another tool in order to look at this. Now I should point out that you could use read ELF for this next step, but you probably don't want to. So we're going to go ahead and use another tool called objdump. The syntax for objdump is pretty simple. Objdump -- disassemble -- M for a machine type, Intel, and then we give it the name of the file. Pipe this to more, and we'll see what I get. So here, it's disassembled the various sections. So it started out with the init section, and here is the code that's being called. Now, a couple of things I should point out. This disassembly is what we call a static disassembly. In other words, if you have some code that's modifying itself or doing something strange, this will not be picked up by objdump. The days of self-modifying code are not over. However, in the Linux platform, it is much less likely that you're going to have to deal with such code because the different memory chunks have permissions, and it is unlikely that you would have a chunk that is writable and executable. So there's some ways of trying to get around that, but fundamentally it's kind of hard, and so you don't see that too much. The other thing you should know about this static disassembly is that if I've embedded some strings in the middle of this code, it might not handle that correctly. Anyone who's ever done any work with DOS disks that are bootable is familiar with the idea of the boot sector, where the first 3 bytes are a jump instruction that jumps over some parameters that are stored about the disk. So this is similar to that situation where if you have anything like that, where you're intermingling code and data, it won't necessarily correctly interpret it with objdump. And we'll show you later how you can do this in some future videos. So back to our disassembly. Here's our init section. We have some pretty simple assembly here. And if this assembly looks like garbage to you or Greek to you, assuming you don't speak Greek, that is, I would highly recommend you have a look at some of the shell coding and assembly courses here at Pen Tester Academy. It might not be a bad thing to have a look at those and then maybe come back to this course. So here you can see I'm subtracting 8 from my stack pointer, and I'm moving some things around, forming a test, and depending on the results of that test, I will jump to 2 different locations. And here we have another section at 400 ACO, and the more interesting part will be when we get into our actual text segment. So what you're seeing here is a bunch of instructions that pretty much say, go here, etc. So this is just a table of jump instructions. It's pretty boring. And here we start our text section, our main program. You can see the address here, 400CD0. It is the start, that's the label. And first, it will do an exclusive OR between the EBP register and itself. Then we have some things that are moved around, and we get into our main program. Some things to note about this assembly: it will call the various functions, and you in particular might want to take note of the different calls, because even if you've done some sort of obfuscation, if you're the attacker or the bad guy that wrote this malware, you will still see that a lot of these things are going to be interpreted. You know, if you're making a standard library call, you can't obscure that name for that function that you're calling, because the compiler has to be able to find it. So here we can see some other code. We have a deregister tm clones. Here we see another function called nmalloc. And again, it's going to call some standard functions such as malloc. So here it says malloc at PLT. So that's just a pointer to that table of instructions that says, please call this malloc library call. Here we have a function called daemonize. Because this binary wasn't stripped, you still have these nice names. Otherwise, you would not. Even if it was stripped, you could still see that it is calling the standard fork process. So it's calling fork that splits off a new process, and it's also calling exit if it's the parent. Without understanding a lot of assembly and just knowing how the fork function call works, you could see that this is a routine that is going to fork a process and then exit from the parent process. So this is a daemonizer. Even if the function name wasn't there, you could see that. Here we have a function called write PID to file. Again, it's very telling. Even if you didn't have the function name, you can see here it says get PID, open a file. There's a call that's being made to write PID to file. Here we see fprint being called, which is going to write to the file, and fclose is being called, which will of course close the file, flush any buffers. Here we have another function called log file. It is opening a file, printing to that file, and closing the file. Here's our main method. So we can see here in our main method, there's some setup. It's going to push the frame pointer. It's going to move the stack pointer to the frame pointer. push it, subtract 8, from the stack pointer. In other words, it's going to allocate space on the stack. And then you're going to see a bunch of move instructions where a bunch of data is going to be loaded onto the stack. And that's in these next few lines. Then you see a call here to nmalloc, a call to put character, popen, fgets, stir. We're doing some comparisons here. And if you look at this code just a little bit, you'll pretty soon figure out what's happening here. And again, we haven't actually run this program yet. And we'll talk about running programs and how you need to be careful when you start doing things like that. But it would appear as though here I'm going to do a comparison, and I do a comparison between what somebody entered and something else, my password, and depending on those results, I'm either going to call daemonize or I'm going to end up calling something else. And here I'm going to write my process ID to the file. I have another call to fwrite. I call log file, fwrite. Looks like I'm creating a socket. Another fwrite call. Here's that htons function, which again is used for translating IP stuff, setting my socket options, binding to a socket, writing some more things to a file, and exiting. Here you can see there's a listen call to flush, accept, stirling, write, etc. So by tracing through this, you can get kind of a feel for what's going on here. Again, you can see if this is making certain function calls, you can tell that it is using sockets because you see some function calls for that. And you can also get a feeling for the fact that it's going to ask for a password before it runs. It looks like if you log on to it, you also have to supply a password. Notice here they have the bind shell password, which is in another segment, which we could easily look up. So we've been able to figure out at a high level what's going on with this particular program without knowing an awful lot about assembly or even how to use a debugger. So we will dig deeper in some future videos, but that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.